What is NerveCenter? It's an intelligent root cause and correlation software. By that, we mean that it goes out and determines the root cause. It correlates information from different pieces of the MIB or from the device and puts it into a single piece of information that can be sent to pagers or to a MOM server. It can take actions for us. It can reboot stuff. It can run command lines. It does it all. It goes out and finds the cause, correlates it together, and makes a determination based on how you program it. In doing so, it increases our network availability. It minimizes the information overload going back and forth. We don't poll all the time. We poll only when information is needed. It does proactive problem identification prior to failures. That's based on traps. If a device on your network is having an issue, it typically will issue a trap. The trap can be received by NerveCenter. It can be interrogated. Varbinds can be read, specific information taken from the Varbinds, and a determination made as to whether it's an interface going up and down, if there's other problems, if you have a high error rate. Any of those things that can be sent as a trap, NerveCenter can receive, interrogate, and make a determination on. Thereby, it increases the availability of your network for you. It does things behind the scenes quickly and only as needed so that you don't bother the overhead or drag down the servers or the network. It reduces or will limit your increase in operating costs. Quite simply, you can use the same amount of staff and increase the amount of work. Why? Simply, if you've got an alarm designed for a group of devices and you increase the number of your devices in the network of that same type of device, you simply add it to the group. They're managed. They're done. You don't need any additional hands or staff to put them in. Just put them in the node list and you can increase your workload. If you've got a new type of equipment that isn't in your network, it can go right in immediately. It can be managed by the standard MIB2 attributes that are found in almost every device manufactured, and you can immediately start looking at it. Again, you don't need a staff to put it in. Just bring it in, put it in the right property group, point the right models at it, and let it start working. As you have time, go off and design your specific models for the specific device, build them, implement them. Again, no increase in staff. Again, minimizes the bandwidth demand for management. That's simple case. Again, we only poll as needed. We wait for information. We're not constantly bombing the network with requests. It works with existing frameworks and platforms. By this, we mean SNMP as a framework. If you have an SNMP capable device, we work with it. If you have a device that only does Telnet or TL1, text language, NerveCenter, through the use of Perl modules, can work with Telnet only or TL1 type devices with a Perl exchange module that you write. Not a difficult piece. Platforms, we work with Solaris, Linux, Windows. That's what we run on. Other than that, if it's got an SNMP agent and an IP address, we'll go get the information. It doesn't matter what the device is after that. But NerveCenter runs on Windows, Solaris, and Linux. Other parts of platforms, if you happen to be an OpenView house and you use OpenView, NerveCenter can coexist with OpenView and send in forms to OpenView. If you happen to be a Netcool house, NerveCenter can coexist with Netcool. It can send in forms directly to Netcool. It can affect the Netcool rules file. So it works in those platforms, sending in forms. It enables rapid integration of new and evolving network technologies. Point-and-click event modeling via the GUI, the graphical user's interface. Again, if you add a new device and you don't have everything there for it, simply point the SNMP standard v2 components at it, and you can manage it. It's extensible using the well-known scripting language Perl. Write Perl modules, write Perl subroutines. implement them, make the calls appropriate for the NerveCenter alarm, and extend your abilities with NerveCenter using Perl. Why would we want to use NerveCenter? I've had people actually ask that question. Why would you want to use NerveCenter? Well, quite honestly, it's a simple SNMP ICMP management tool. Point the node at the right alarms, and I can manage the SNMP and the ICMP status of that device right out of the box. NerveCenter has the alarms pre-built in the default configuration to manage SNMP and ICMP status for just about any node on the network. It does advanced correlation. Advanced correlation in the form of persistence. Has this happened over and over and over again? NerveCenter can keep track of that. If it happened once on Monday, once on Tuesday, and 3 times on Thursday, that could be an alarm, an event of interest to you, and NerveCenter could have remembered that for you. And it will alert on that. Advanced correlation, time, and persistence, or a sequence of events. NerveCenter can alarm on a sequence of events. That's another part of the advanced correlation. This happened, and then that happened, and then this happened. That's an event of interest. NerveCenter can inform you on it. It's extensible and customizable via Perl. If you have Perl background, you will love this capability. You can download Perl modules from cpan.org, input them into the NerveCenter environment, and use them. That's why I can say we can talk with Text Language 1 or Telnet, because people have already written those modules. They have already been imported into NerveCenter by other customers and utilized, and they work well. It's scalable. NerveCenter is scalable from 50 nodes to 50,000 nodes. NerveCenter supports the distributed architecture in that you can have a structure of NerveCenter servers managing remote locations and reporting back to a manager of managers in upper-level NerveCenter. They communicate via informs, guaranteed delivery, so you're not going to miss the information. It's distributable. It's scalable. And it integrates, again, with frameworks and platforms. ICMP, SNMP, Perl modules, platforms like Windows, Solaris, and Linux for operating on, and any device out there that has an SNMP agent. We're all familiar with information overload. If you guys have got consoles for Netcool or OpenView, you're familiar with the event consoles where you see critical events, normal events, warnings. You get redundance, you get secondary faults, you get false positives, all being bombarded into the Network Operations Center, the NOC. Here's where NerveCenter comes in. You can put a NerveCenter server between your NOC and all of those devices on the network and let NerveCenter do the filtering, the checking, the deduping, the removal of false positives, and have it send to you only the information that is of importance. Example, if you've got a server farm out there on that branch for servers, and there's 200 servers out there, and all 200 of them go down, you don't want to see 200 informs at the Netcool console that you've got 200 servers down. The reality is you probably lost a link or a router or something that goes to that server farm. If NerveCenter is in the middle, NerveCenter can interpret that information, go out and poll specifics for the router to see if in fact it is down or if it's lost its link or something of that nature, make a determination, and come back and send one inform to the upper level console that says the router is down to server farm A. You don't have to see 200 events, you get one. So that's where NerveCenter comes in. It can do the same thing for applications, routers, hubs, servers, individual PCs, all these devices that are on your network. NerveCenter can filter, isolate, interrogate, correlate, and inform for you. How do we do all of this? What are the key elements that we use? Here is the list of the 5 major things that NerveCenter does for us Its first thing is that it does smart polling. We only poll when we need data. There is no sense to go out and poll a 1200 interface table on a Cisco router if there's no problems with it, or if only interface 100 is having a problem. So we will only poll when data is needed. We do trap-directed polling. We adjust the frequency of our polling based on events that we receive. What that means is, if I'm polling every hour for link up, that's probably a decent rate, and I make sure the link is up every hour. If, however, I receive a link down trap, and it's one of my primary links that I need to manage, I don't want to sit there and poll that status every hour. I want to know quickly that that link down means something or that it came back up. I adjust the frequency. NerveCenter adjusts it. We compensate for it by writing a poll with a different frequency to go out, and it goes from being polled once an hour to once every minute. Are you there? Are you there? Are you there? It waits for that link to come back up and notifies us that it's back up so that we're not waiting the hour for the notification. We switched over to the frequency based on a trap that best works for our network and the determinations that we need to make. Trap-directed polling. We do distributed polling. We poll locally or regionally rather than across a wide area network. Individual NerveCenter servers can be set up for anywhere from 50 to 100,000 nodes. If you have a small location of 200, 250 nodes, you would want a separate NerveCenter server managing that location, taking all the information, running that situation, and only when there is a major situation on that network would you want to inform the manager of managers, the upper-level NerveCenter server, that there is something that's gone wrong. And that would be done with a NerveCenter to NerveCenter inform. Guaranteed delivery mechanism. It's an ICMP packet. It's going to get there. So we can distribute our polling. And the cost of distributed polling is not that expensive. Localized trap processing. The traps that are processed locally or regionally don't get lost across a wide area network. For those of you familiar with SNMP and traps, traps are an unguaranteed delivery. They're broadcast out to either a list or to a network ID and forgotten about. They're not guaranteed to be delivered, so if they get dropped, you could have lost an important piece of information. With distributed machines, those traps are processed locally so that that machine catches them on the local network, works with them. If it's an important piece, it sends it again via an inform to the upper-level NerveCenter manager. So you don't lose localized trapping, and you don't have to try to send traps over a wide area network. We do selective table polling. There's no need for us to poll a full table when we only want to know about specific instances within that table. My previous example, a Cisco router with 1,200 interfaces. One goes down. I don't want to poll 1,200 to find out the one that's gone down, so I'll typically get a trap. I'll interrogate the trap varbinds, and usually inside the varbinds, I will find a piece of information that says what interface it is. Using a subobject scope alarm, I will instantiate a model based on the instance, the specific number for the interface, and I will go interrogate that interface and all of its components across the various tables that I deem necessary, and I will create a correlation model that I will then inform on or take action on. Again, 1,200 interfaces, interface 100 goes down or has a problem or displays high utilization. There's no need to go get all 1,200 entries. I can focus on interface 100. I can go read the appropriate MIBs and look at traffic levels, high, low, 2-minute, 5-minute periods. You can make determinations and I can inform on that. And we do that with selective table polling. Advanced correlation types. Once NerveCenter has determined there is a problem and it goes out to get information, we have these different types of correlations. We can suppress, do sequence, do time-related, or do an associative. Suppress. We can suppress secondary faults. The example here, we could suppress frame PVC errors if the frame access service is actually down, access circuit is actually down. So we have a suppressive correlation. We have a sequential correlation. We correlate based on a sequence of events. Is the interface operationally down? And is the type of interface is an Ethernet, and it was previously passing traffic, then this is in fact an important link down situation to our network. A sequence of events. Temporal. Timing and persistence. The example here is a good one. Consecutive superuser attempt failures from a specific user over a specific period of time. Notice I didn't say 3 in 2 minutes. That's what most people think about or would think about. I can do 5 in 4 minutes. I can do whatever you want. 3 in 2 minutes, 2 in 1 minute. NerveCenter has the ability to change this and make this work for you. Time and persistence. Did I get too many link up, links downs in a period of time? Then I've got a link that's chattering. And the final correlation methodology is the associative, where we associate separate events into a single event. The example here, we associate that the status of 2 ISDN-B channels to derive that a single BRI status event has happened. We associate. We can also associate a login failure from one user a couple of times, and they just fall under our 3 and 2 minute category, but then followed shortly thereafter by 2 failures from another user. We can associate those 2 together to be a potential attack. So there is lots of ways to associate. Associate all kinds of things, interfaces, status, events. So there are the advanced correlation types. What happens inside of NerveCenter? On the left-hand side, we have our input from devices and applications out on the network. We have SNMP-enabled devices and different applications. Now, with an SNMP-enabled device, I can send a poll. A poll is a request for information. Send me back a specific attribute from a MIB location. So it is bidirectional. I make a request, I get a response. A trap. Traps are unidirectional. They come from the device, they're thrown out on the network, and they are sent out for all to hear or specific servers to hear if the list has been so defined. When an event happens out there on those devices and applications that NerveCenter is interested in, we call that a trigger. And that trigger comes into NerveCenter. It comes in by either we've written a poll to ask for it, or we have a trap mask written that is watching for it. Either way, it comes in, it's evaluated to true, and the trigger is instantiated, and it's put into memory along with the alarm. And that's what happens there in the center. We process our custom rules and thresholds and such when the triggers come in. In this particular case, we were looking for a trap trigger. When it came in, it moved the alarm off of ground to the first state the state in yellow called got trap. The fact that it says it's a trap trigger tells me it was from a trap mask. The outgoing portion of got trap is a poll trigger, so that tells me that it comes from a written poll. We are going out to check information. Based on that information returning its evaluation as true, we fire that trigger. We transition from got trap to got error. So the key things here are triggers, because they move alarms along, and where the triggers come from, either polls or masks or Perl subroutines or other such places that we will hear about. When the trigger is detected, it moves an alarm, a behavioral model, off of ground, instantiates it or puts it into memory, and keeps track of it until it returns to ground, where it then gets removed. Our job as network engineers and as NerveCenter people is to write the trap masks and the polls that fire these triggers when they evaluate, then to use those trigger names that we generate to create the transitions in the behavioral model so that we can account for the action and activity that we want this behavioral model to do for us. On each of the transitions, the transition from ground to got trap or the transition from got trap to got error, we can take actions. And in that transition, we create a list of the actions that we want to take place for that transition. Some of the possible actions are log the data, create an email, send a page, inform one of our platforms, run an action router rule. We can set an attribute. We can send other traps. We can do SNMP sets. We can run or execute commands from the command line where we actually exec out and run a command line function. And we can run Perl subroutines. And this is how we put together a NerveCenter behavioral model. We take all the pieces that we write, a poll, a mask, the trigger names that we give them. We take those and we create behavioral models that transition, that create the actions and activities that we want for the behavior needed for the situation. We put them all together, we turn them all on, and they become a behavioral model. All the components become a behavioral model that manages or monitors a specific behavior that we have built for. So, we're looking at a NerveCenter action. It's in action. A trap of interest comes across the network. This trap happens to be from a Cisco device. A generic type trap 2 comes in. NerveCenter has a trap mask. We wrote this trap mask. It says to sit there and listen for an enterprise ID of 1361419, meaning Cisco, and listen for it to be a generic type 2. And when that matches, fire off a trigger. And the trigger name we give it. We, as engineers, write these trigger names. We program the trap mask. We give it a trigger name so that when the condition evaluates to true, it fires that trigger. That trigger we take and we make an alarm. We create a state. We add the transitions with the trigger names associated to them, and it transitions from state to state for us. When the mask evaluates to true, it fires the trigger. It causes a transition. The transition occurs in our state diagram. And when that transition occurs, it's put into memory, and it is tracked for us. We can see it in the alarm summary display. We take actions during the transition. The actions could be to email somebody, to send an inform off to a platform like OpenView, to restart a process that's on another machine that sent the original trap to us? We don't know. We could create a trouble ticket on remedy systems, and so on. There is a long list of actions that we can take during a transition. So that's what happens inside of NerveCenter. That's how it happens, the logic, how it flows. A trap comes in. We have a component, a piece of our puzzle written that's called a mask. It's turned on. It's waiting there and listening on the network, and it listens for a specific event. In this case, a Cisco 2.0 trap, a generic 2 trap. It fires a trigger. That causes a transition. The transitions take the actions that we program for. It's all done via a point-and-click development GUI. You guys know it probably as the NerveCenter client. The client utility is where we build everything. We build masks. We build polls. We build node lists. We write Perl subroutines. We create action router rules. All your ongoing work is done via the client utility. The admin utility is used to set up your server initially and make only those changes that need to remain permanent to the server. In other words, I install NerveCenter and I go into the admin, one of the first things, and I make sure I got my license installed. I make sure I've got my SNMP values set the way I want them. I'm telling it where to put all my log files so that that's consistent. I'm telling it where my pager list is because that's consistent. I'm telling it where my mailing list or my mailing host is so that that's consistent. And I save those settings and I close the administration utility. I don't use it that often. Then I open my client utility and I go in and I start building my components, my pieces that eventually I turn on. And when I get all the pieces turned on, I have created a behavioral model that models the behavior I want to take. It's all done with point and click. Here is the list of actions that NerveCenter can take. Action routers, an alarm counter. It can beep. It can send a clear trigger. It can run a command line function. It can delete a node. It can write to the event log on the server. It can do a fire trigger of its own. It can send an inform OPC, which is a type of OpenView platform. It can do an inform platform, which is netcool. It can do a log to file. It can create a log to database. It does mail, Microsoft Mail. It writes notes to itself. It'll do paging. It'll run Perl subroutines. It'll send another trap or send a trap to another device. It'll do a set attribute. And we'll talk about set attributes because there's some things that are funky in there, but we'll talk about those. We can do SNMP sets, and we can do the SMTP mail server. We can send a piece of mail. So there's really a lot of stuff that we can do here. This is the list of actions. So looking at this again in the distributed architecture that we were talking about earlier, you've got a network cloud. And you've got some remote NerveCenter servers along the bottom and one upper-level platform and one upper-level NerveCenter server. What you would ideally want here is you would want all of those devices or networks, NerveCenter servers at the bottom, to run locally, taking care of all the local trap processing, the handling of the day-to-day stuff, turning off and on alarms, making things happen at the local level. But when something important goes on that affects everybody or is determined to be of higher level importance, it sends out an inform either to the platform or to the NerveCenter server, your choice, or both. You can get an inform up to the platform that says it looks like this group of servers is down. And you can send the same thing over to NerveCenter's main piece where it can keep track of that and say, if this happens too many times, I'll create my own inform up to the platform that we need to send somebody down there to look at it. So we have both ways. So in a distributed architecture, this is the way NerveCenter would work. Separate servers, running locally, processing traps, handling the day-to-day stuff, handling the models, handling the alarms. Good question suddenly comes up. How do I deal with all these models and alarms at those remote locations? Well, that's pretty straightforward. If you are, for instance, at the nerve center at the top center, and that's where you do your daily job, and one of the things you do is you develop or you modify nerve center alarms as needed to make changes that affect the remote locations shown down here at the bottom. How do you get them from your server to one of the remote locations? Quite simply, server to server, put the signals, put the models, distribute them out there right from your console, and they're on the remote machine for you. Done over the network. You don't have to go copy files. You don't have to do anything. Connect, export it to the server attached, and it's on the remote server. So it's easily managed from a centralized location. Online documentation. Believe me, if you need information and you are on a page inside of the NerveCenter client or the NerveCenter admin utilities, there is a help sensitive button on that page. And that help sensitive button will open for you online documentation and tell you what's going on that page, what settings you need to make, and most likely the changes and the possibilities that you can make to those settings. There is a wealth of information in the help. The help is built in. It's turned on. It's modified every time we make a release, every time we make a change. It's constantly updated. Learn to use the help. There's even examples in a lot of cases. Online documentation. Great stuff. And you don't even have to be connected to your NerveCenter server to use it. If you have your client on your machines right now and you did start programs, open service NerveCenter, and you clicked on the client and you opened that client application in front of you right now, you could go to the top line where it says File, Edit, View, Favorites, Tools, and Help. You could click on Help, and you would get the help files and all of the information and a search tool and online manuals and everything you need. And you're not even connected to a server. NerveCenter is shipped with what we call behavioral models. Again, the behavioral models are all the pieces put together, turned on to create a behavior managing situation for us. NerveCenter is shipped with a group of them, ones that we have considered to be old favorites or standards. Do they meet everybody's needs? Probably not. Do they meet the majority of the needs? Definitely. And they're in large categories such as authentication, data collection, interface status, node status, and so on. And in each of those categories, there are individual alarms. For data collection, there's an all traps, there's a gateway list, there's a IP sweep, there's no sysinfo. You can load these. Are they all loaded at the moment you start NerveCenter? No. A select few of them are when you do a default installation, sure. I think there's about 11 of these that get loaded. Can you load them? Absolutely. Anytime. Load them, put them in, take a look at them, copy them, use them, reference them. Say, this does what I want it to do, but I need it to do it just a little bit differently. Copy it. We don't care. That's what they're there for. They're examples. They're working examples, and most of the time they'll work for you. There's troubleshooting. There's vendor-specific models. There's all kinds of things. NerveCenterisms, as we call them. A poll. A poll is an SNMP request for information. You write the poll using base objects. The poll evaluates to true, and when it evaluates to true, it fires a trigger. The poll is one of our most powerful pieces of the toolkit in that we get to tell it what to give us for information. The information is very specific according to the vendor that we are working on, or as generic as System 2 MIB2 objects. A mask. A mask is a nerve-centered tool that we write, and we fill it in so that it listens on the network for traps. Traps are unsolicited network events that a device emits when something has happened, and it's usually broadcast or sent to a direct list. NerveCenter's mask listens for that by an OID, a trap ID, and other specific things. Once it's listened for, the mask triggers a fire trigger. We write the mask, we fill in the pieces, and we tell it the name of the trigger to generate. So a mask is, again, a nerve-centered tool for catching traps. A trigger. A trigger is the function that we most often need to create. We create triggers so that the trigger action moves the behavioral model or the alarm state diagram from state to state based on a condition having been evaluated to true. Whether it's a mask, a pole, or a Perl subroutine, we create triggers. We name these triggers in such a way that normally they mean something to us. If I were to have a trap mask written that would catch link up, I would probably want to name the trigger link up. I don't think I'd want to call it cold start or Cisco bad or damn thing. And I've seen them named that way. So that's why I say something. So let's name our triggers so that they mean something to the system and to us and to the people who follow us. So the trigger is the mechanism that moves us along. We write the trigger names based on operations that we create in a mask, a pole, or a Perl subroutine, and then we use the trigger to move our state diagrams, which we call models, and that we build using the triggers. Trigger. A transition. A transition is the movement from one state to the next. The transition is caused by the trigger being fired. The condition evaluated to true, the trigger was fired, the trigger was a pending trigger because it was everything was turned on and it was the next active transition that could happen. Therefore that trigger fires and it causes a transition. The transition is a little square oblong box that goes between the state diagrams. We fill in the name of the transition, or the transition's name is given the name of the trigger that fires it. So in the case of a link down trigger, we could move from ground to state 1 on a transition whose name is named after the trigger link down. Now the other part about a transition is that it has all kinds of actions that we can assign to the transition so that they happen when the transition is fired, when the transition happens. So we're going to hear a lot about transitions and triggers and things. State. The state is a holding place for NerveCenter to watch for pending transitions, triggers that are waiting to be fired. We have a state called ground, and then we have all kinds of other states that we can name ourselves when we design our behavioral model. The state is, as I said, a holding place. It doesn't do anything but wait for the pending transition. Now when I look at some diagrams, alarm diagrams, I see that there are states with lots of transitions hanging off of them. I showed you one yesterday. It looked a little confusing. And the key to all of that is NerveCenter is directional. You have to leave a state and follow an arrow going out through a transition and into another state. If the arrow is coming in, it's not a pending transition because it's the one that's coming in. You can only have a pending transition on an outbound transition. Keep that in mind, because that way it's easy to follow what's going on in NerveCenter when you follow the arrows. Follow its directions. An alarm definition or state diagram. Once we've created our masks and our poles and we've given the triggers that we want to use, the names that we want to give them, we need to take that to an alarm definition or a state diagram and create the states that will be waiting for us, and then the transitions that will be used to transition from state to state. So that is the alarm definition, is the picture that shows the states and the transitions for us. It's another part of our behavioral model. All of these are components of a behavioral model. An alarm instance. When the alarm has been removed from ground, ground is a non-memory state. It is not tracked. Once it comes off of ground or removed from ground, via a transition based on a trigger, it gets put into memory. Once it's in memory, we call that an alarm instance. It gets tracked in the alarm summary. And each and every alarm gets tracked. You can have as few as just a couple of alarms in memory to as many as several thousand alarms in memory. It's all up to how you have built your NerveCenter server and are using it. So an alarm instance is an alarm that's being tracked in memory. Why is it being tracked? We track the triggers that got it there, the time that it went there, the actions that it was taken, and give you a diagram so that you can follow through and see the logic behind it and keep up with it if there happens to be a question in the logic. The alarm summary will be, the alarm instance in the alarm summary will be one of your best used troubleshooting tools when you have an alarm that you are building and it doesn't seem to work. It gets to a state and stops. You can trace it to that state, and when it's in that state and you have a transition pending that'll take it out and that doesn't fire, then there are a set of rules that you can look at to see why it didn't fire the trigger. And you can trace it through and make it work for you. So the alarm instance is an important piece, and it's shown in the alarm summary. The next is a subobject, and this is a very important concept to get a hold of. If I'm talking to you about a Cisco switch, that's a single node. NerveCenter has a license that's licensed by the node. But you and I know that that switch has many, many interfaces. Could have 1,200, 1,500, however many interfaces. If I want to track each interface, then I have to look at the subobject. Meaning, if I were to look at the IF entry table, and I were looking at IF entry .16, I would be looking at subobject IF entry 16, meaning the 16th entry in the interface table, and that's the one that I'm tracking. So a subobject is the table or variable that you're tracing and its specific number. System.0 is a subobject. IF entry .16 is a subobject. LIF entry .200 is a subobject. It is comprised of a base object from the pole and the specific instance in the table that you are looking at. A subobject. Okay? This gives us the ability to take something like a trap from a Cisco switch, interrogate the varbines. The varbines may tell us that there's an error on interface 200. We can turn around and fire a trigger with a subobject of IF entry .200, causing a transition in a behavioral model. That transition takes with it the information that we give it, in other words, IF entry .200, to the next state. And in that next state, we could have a poll waiting to be run and look at a specific instance in the interface table for information, and it would get its entry from the information that came to it on the previous transition in the form of its subobject. I take a trap from a node, and I can focus the very next state to a poll on an interface by using the subobject and telling it which one to focus on. The next thing we talk about, we hear a lot about, are property groups. Property groups are containers. They hold properties. Properties can be base objects of MIBs or user-defined terms. The key thing about a property group is to know that it's a container. It contains properties, and those properties are either base objects or user-definable terms, and every node in our node list is assigned to one and only one property group. You may have a property group for Cisco. You may have a property group for Metaswitch. You may have a property group for Solaris. In those property groups, those containers are specific base objects for Cisco, Metaswitch, or Solaris. And it helps us focus the alarm, the poll, and the information onto only the objects that that device needs to respond to. A property group. And the last thing is the behavioral model. The behavioral model is all the pieces put together, turned on, and running on your server. Say, for instance, you have a model that needs to catch a trap, turn that trap into a subobject, and poll for the interface. That means I have to write a trap mask. I have to turn it on. That's one component. I then have to write a poll. The poll will fire a trigger. I turn that on. I take those two pieces now that they're turned on. I go to the alarm definition window and I start designing the alarm definition, the state diagram that takes the actions I want appropriate. I create states. I add the transitions based on the names of the triggers that we've generated. I turn it on and I wait to see if it works. All of those pieces, the mask, the poll, the alarm, they are part of the behavioral model. The other part is the property group. If the node I want to run this particular alarm definition on isn't in the property group that has the base objects for the poll that I wrote, it will never run. So I also have to incorporate the property groups to match the node to the poll, to the mask, to the alarm. That's another piece of our behavioral model. When it's all turned on and all the components are in place and working, it is a behavioral model. SNMP terms. If you saw interfaces IF table, IF entry, IF type .2 equals a 6, could you tell me what that translates to? I can tell you right now, interface 2 on this device is a CSMA-CD, an Ethernet interface, from looking at it. But here's the important parts of this ISO terminology to NerveCenter. IF entry is called the base object. It's the base of all kinds, a bunch of attributes that can be sought out and have information after this IF entry, after the base object. The next is the attribute. That's the IF type. So I have a base object, dot attribute, and then the next, the .2, is the instance within the table, .2, .100, .600. And then the final is the value that is contained within that instance of the attribute. These are the 4 parts that NerveCenter relies on for nearly everything based on SNMP that it does. You have a base object, an attribute, an instance, and a value. I can create or concatenate, if you will, a subobject from this statement. The subobject here is ifentry.to. Not iftype, but ifentry.to. You extract the base object and the instance to create the subobject. That's what gets passed on. Remember how to do that, because you'll be doing that frequently. You'll be creating subobjects and understanding them by pulling out the base object and the instance. The NerveCenter subobject in this case is ifentry.to. The base object and the instance. A value is contained within an instance of an attribute which is part of a base object. When I look at the attribute and the instance, it's like going to the post office and walking over to a specific post office box that's labeled ifentry, iftype.to, and I open that mailbox and find that there's a 6 in it. The last piece of this is I can take the phrase system.sysdesker.0 equals HPUX, which is just like the phrase up above, ifentry.iftype.to equals a 6, and I can extract from it its subobject, which would be system.0, correct? The base object and the instance. What is there that is special about an instance of 0? The instance of 0 means that there is one and only one of them. If you see a subobject of 0, there are no others. It's not a table. It's a single object. System.0 is a single object. ifentry, on the other hand, could have any number in it, from 1 to God knows how many, depending upon the device. So there's nothing special about it because that's a table. But if it's a 0, you can be assured that there is one and only one of them. The information, the management information base, the MIB, looking at them, 1361 gets us to the structure where we need to decide whether we're going with a management or a private or V2, whatever. 13614 is a famous one that we have to follow. It gets us into the private. It's 13614. One puts us into a private enterprise specific, and then after that there are numbers for specific vendors. 1361419 is Cisco. 13614-178 is NerveCenter. Last time I checked the IANA, there was over 36,000 private enterprise OIDs. 36,000 vendors with their own special area. So when you're dealing with a vendor, know their area, get their MIB. 136121, MIB2. It is a standard. Get used to it. 13612. Every device manufactured responds to the standard MIB2 management section. I don't care which one of the 36,000 vendors it is, it's supposed to respond to these. This is the base standard MIB2 management. This is what makes NerveCenter capable of taking any device off the shelf that is SNMP compliant, throwing it on a network, and managing it, because we can look at its standard management MIB2 attributes and manage it. The MIB2 section is broke down even further. Now I'm only showing 11 possible areas, but the last I knew there was like 130 some of them now that are under the standard MIB2 management. Everything from ATM to serial line interfaces are all under the standards now. Again, MIB2 standards, 136.121. 1 is system, 1212 interfaces, and so on. Walking the MIB. When you get to these areas underneath them, there are subs, and there are attributes of those subs that you can go get, look at, read, use the value that is there. SNMP v1 is the standards. It's unsecure. SNMP v2 has a challenge packet that goes back and forth, but it is still fairly insecure. SNMP v3 is, however, a secure portion of the SNMP protocol. Requests, acknowledges, challenges, chaps, acknowledgments, passwords encoded, encryptions, triple DES, different key structures, different user contexts, all kinds of possibilities to create a very secure environment for passing SNMP attributes. NerveCenter does this very well. NerveCenter communicates, that is, it will send and receive polls with an SNMP v3 agent on behalf of a very specific NerveCenter user in a very specific defined context. NerveCenter supports at least 3 security levels of communicating with SNMP v3 agents. It supports the HMAC MD596, the HMAC SHA-96 SHA, and the Authentication Protocol CBC-DES. There are also user contexts, user 1, user 2, and individual user contexts. You need to work closely with your network engineers if you are using SNMP v3. You and your network engineers need to be able to exchange all of these pieces of information between the device and the NerveCenter server so that NerveCenter can appropriately get the SNMP attributes from that v3 device that you want it to get. The note there, or the bullet, a node must have SNMP version information before NerveCenter can even poll it. If you don't know what it is, NerveCenter can automatically go out and challenge it and find out what its highest level of version, SNMP version support is. It can go there and discover that for you. It'll process traps based on what it discovers. It'll classify the node for you. If you choose the default, which is v1, everybody that I know of works with v1. An SNMP v2 node will work with v1. An SNMP v3 node will work with v1.